In 7.3, what we're doing is still linear programming, but now we have to come up with our objective equation and come up with our constraints. So we have to look at a situation and then come up with those equations instead of inequalities. So I'm going to be following along with the examples from the book that start on page 405. This is the example 1. We have a 4-H club member who raises goats and pigs. She wants to raise no more than 16 animals, including no more than 10 goats. She spends $25 to raise a goat and $75 to raise a pig. She has $900 available for the project. Find the maximum profit she can make if each goat produces a profit of $14 and each pig produces a profit of $40. Well, first, before we start writing the equations, we need to look at what we're trying to do and what we're trying to solve for. So here we're trying to maximize profit for each goat and each pig. That tells me that I want to let X equal the number of goats and let Y equal the number of pigs. Now I could have easily chosen Y to be goats and X to be pigs. Just for sake of consistency with the book, I went ahead and chose X to be goats. So now we're going to look at our equation here, or we're going to look at the problem here. We're going to come up with our objective equation. The objective equation is what I'm trying to maximize. So I want to know the maximum profit, and I know the profit for each. So I'm trying to maximize sorry, that looks horrible. Let me use my text pen. Okay, I'm trying to maximize my profit and my profit of each is $14 for each goat and $40 for each pig. So I know that's 14 times X plus $40 times Y. Now, I'm not really going to write it as an equation because it doesn't necessarily matter that it is an equation. What matters is that we get what we're trying to maximize. And I'm trying to maximize this quantity, whatever this ends up being after I find my corners. Now I need to work on getting my constraints. So my constraints come from the rest of the information, and they're a system of inequalities. Okay, so let me resize this. So I know from the situation that she wants to raise no more than 16 animals. That means that however many animals she has, 16 is the largest amount. So if she has so many goats, that's the amount of X, and so many pigs, that's the amount of Y. So I'm going to have x plus y can be no more than 16. So x plus y has to be less than or equal to 16. So there's one of my constraints. Okay, I also have that she wants to raise no more than 10 goats. Well, x is the number of goats, so x can be no more than 10. So x has to be less than or equal to 10. I also know from the problem that it takes $25 to raise a goat and $75 to raise a pig. So, and I also know that she has $900 available to spend. So I have that cost equation that says 25 times however many goats she has plus $75 times however many pigs has to be less than or equal to 900. So here's my system of inequalities. Now I also know, because she can't have a negative amount of goats and a negative amount of pigs, that I also have the constraints that x and y have to be bigger than or equal to 0. So here are my system of inequalities graphed. This is my x greater than or equal to, x less than or equal to 10. Here is x plus y less than or equal to 16. And here is 25x plus 75y is less than or equal to 900. So what I need to do is I need to find my feasible region. And remember, my feasible region is the solution to the system of inequalities. So now that I have my lines graphed, I need to find out where I need to shade. So here, I know I'm going to have x less than or equal to 10. So I know I would shade to the left of that line. I know that x plus y has to be less than or equal to 16. So I know if I test 0, 0, I'm going to shade below that line. And I know also that 25x plus 75y is less than or equal to 900. So that tells me that I am shading below. So now I know exactly where my feasible region is. It's where all three of those solutions overlap. So I'm going to erase what I don't need here. And I see here my feasible region is contained in kind of this pentagonal shape here. Now from this, what I need to do is find my corners. To do that, I'm going to go ahead and delete this so that I can work a little bit. So I need to find my corners. My corners are just the vertices of my feasible region. So I have a corner here, 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 and here. So I need to find what those corner points are. So I'm going to use my skills with intercepts and linear equations to do that. So I know my corner here, my vertex here is my origin, 0, 0. I know that this corner right here is represented by the x-intercept of my vertical line, which is 10, 0. I'm going to skip to this y-intercept over here. I know this y-intercept is the y-intercept of my line 25x plus 75y is less than or equal to 900. So I know that that is going to be 0, 12. So my y-intercept there is 0, 12. Now I need to figure out what the other two corners are. That's where I'm going to use my knowledge of linear equations from previous courses, Algebra 1 and Algebra 2 and so on. So I'm noticing here this is the intersection of my two lines, x plus y equals 16 and 25x plus 75y equals 900, which in the book that they've reduced that to x plus 3y equals 36. Now, from our previous chapter, we learned how to solve these with matrices. It becomes very easy to do. 1, 1, 1, 3. I take the inverse of that times my answer matrix here. So 1, 1, 1, 3 and 1636. Once I solve that in my calculator, I get that my intersection is 610. So that's how I would find the corner there. Now, of course, you can use your other methods from Algebra 1, solving by substitution or elimination. Those work just fine. You'll come up with the same corner. Now, my other corner here is the intersection of my vertical line, x equals 10, having some issues with my stylus today. So x equals 10, and my line x plus y equals 16. So I can substitute 10 in for y, 10 in for x, and solve for y. So subtract 16 from both sides, and you get y is 6. So I know my point here is 10, 6. Now that I've found all my corners, my next step is to test my corners in my maximization problem, so in my objective equation. If you remember, my objective equation was maximizing my profit when I have $14 for every goat and $40 for every pig. So when I have those profits, I want to see which one of these corners will give me my maximum profit. Now you can see this from the table on page 406, how they've plugged those corners in. So you can see if we test the point 0, 12, that means I'm plugging 0 in for x and 12 in for y. 12 times 40 is 480, plus 0 is 480. Now, we can try the other points. If I try 0, 0, it's pretty obvious that 0, 0 is not going to give me my maximum. If I'm plugging in 0 for both x and y, I'm going to get 0 for profit. If she doesn't raise any animals, she doesn't make any profit. Okay, so we're going to try our point 6, 10. So that's 14 times 6 plus 40 times 4. 14 times 6 is 84. 84 plus, excuse me, that should be 400. So times 10. So 6 times 14 is 84, plus 40 times 10 is 400, so that's 484. And if I keep trying points, we'll see that 10, 6 gives me 380, and the point 10, 0 gives me 140. So we can see my maximum occurs at 610. That means that we have a maximum profit of $484 when she raises 6 goats and 10 pigs. Okay, so what we've done is, I'm going to just recap a little bit. What we did from the beginning is we looked at our problem situation, figured out what we needed to maximize, which was this equation here, and then from the rest of the information in the problem, we set up our constraints. We graphed those constraints and found our feasible region. Once we found our feasible region, we found our corners and then tested our corners in our objective equation, which was the one we needed to maximize. Okay, we're going to be looking at example 2 next. Example 2 is an office manager who needs to purchase new filing cabinets. He knows that Ace cabinets cost $40 each, require 6 square feet of floor space, and hold 8 cubic feet of files. On the other hand, each Excello cabinet costs $80, requires 8 square feet, and holds 12 cubic feet. His budget permits him to spend no more than $560 on cabinets, while the office has room for no more than 72 square feet of cabinets. The manager wants the greatest storage capacity within the limitations imposed by funds and space. How many of each filing cabinet should he buy? Okay, so what we're trying to do here is we're trying to maximize our storage capacity. Storage capacity is in cubic feet because that's volume, so you need to be able to recognize the relationship there. It also gives you more hints about what the constraints are going to be. Your limitations are imposed by funds and space. So we're going to have a funds constraint and a space constraint. Sorry, that was my phone. We want to know how many of each filing cabinet he should buy. So we know we're going to let X and Y be our types of filing cabinets. So we're going to let Ace be X, and Y Excello. So now we need to figure out our maximization problem, or our objective equation. We want the greatest storage capacity. So what information in the problem tells us about the storage capacity? Well, the storage capacity is the cubic feet. So we see here our Ace filing cabinets hold 8 cubic feet. Our Excello hold 12 cubic feet. So we know our objective equation, or what we're trying to maximize, is going to be 8 times X, and 12 times Y. So that is my objective quantity. That's what I'm trying to maximize. Here I want to know how many of each are going to give me the maximum storage capacity. Now I know I'm going to have limitations imposed by funds and space. So I know I'm going to have constraints on each of those. Now notice here it doesn't give me a quantity constraint. It doesn't say he can only buy 20 cabinets. We don't have that restriction here. We do know that he has to buy at least 0 cabinets. So we do know we're working with positive numbers, and we're only working in our first quadrant, which you can see here. So I know from my problem here, my cost limitation is that each Ace cabinet costs $40. So that's 40 times X. And each Excello cabinet costs $80. And we know he has a total of no more than $560. So I know that's less than or equal to 560. I know I also have a space limitation here. So I know that the Ace cabinet takes up 6 square feet and the Excello cabinet takes up 8 square feet. And that can be no more than 72 square feet. Okay, so what we've done here is we've come up with our constraints. And again, we also have the limitation that we can't buy negative amount of cabinets. So we know X and Y both have to be bigger or equal to 0. And so we're going to graph our equations here based on my X and Y intercepts. So again, you can reduce these equations. You can notice that the 40, 80, and 560 all can be reduced at least by a factor of 10, if not by a factor of 20 or more. But I'm just going to use what I know here about X and Y intercepts. I know if I want my X-intercept, I just have to cover up Y. So I'm going to pretend my Y term isn't there for a minute. and divide 56 by 4. So I know my x-intercept there is 14. I've graphed that here. I know my y-intercept for that. If I divide 560 by 80, I get 7. So that I've graphed that y-intercept here. 6x plus 8y less than or equal to 72. 72 divided by 6 gives me my x-intercept, which is 12. So that is this point here. And 72 divided by 8 gives me 9, which is this point here. Okay? Then I know I'm going to need my feasible region, so I'm going to figure out where I need to shade. I know I'm less than on both of these, so I know I'm going to be shading below on both lines. Where those overlap is where my feasible region is going to be. So I know I don't have these regions. But I do have this quadrilateral region here with the following corners. Here, 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 and here. So now I'm going to use my knowledge of linear equations to help me get those. So I know my intercepts pretty easily. I know this is 0, 0. I know this was the x-intercept of my equation 6x plus 8y equals 72. So I have that my intercept there is 12, 0. I know this y-intercept here was 0, 7. And to find this right here, it's the intersection of my two lines. Again, I can use matrices really easily here. And have 40, 80, 6, and 8. And do my matrix equation, A inverse B, that we did a lot in the last chapter, to solve that equation easily to get that this is 8, 3. Now that I have all four corners, this is where I need to maximize my objective quantity. So let me erase and get rid of some junk here. I'm now going to plug in my corners to that objective equation. So when I plug in 0, 0, I get 0. When I plug in 0, 7, I get 8 times 0 plus 12 times 7, which is 84. I have 12, 0, 8 times 12 plus 0, that's 96. And 8, 3 is 8 times 8 plus 12 times 3. 8 times 8 is 64. 12 times 3 is 36. 64 plus 36 is 100. So I can now see where my maximum occurs. My maximum occurs at 8, 3. So the maximum storage capacity is 100 cubic feet, where he has bought 8 ACE cabinets and 3 XLO cabinets. All right, our last example is about a laboratory. Okay, we have certain lab animals that must have at least 30 grams of protein and at least 20 grams of fat per feeding period. These nutrients come from food A, which costs 18 cents per unit and supplies 2 grams of protein and 4 grams of fat. Food B contains 6 grams of protein and 2 grams of fat, costing 12 cents per unit. Food B is bought under a long-term contract requiring that at least 2 units of B be used per serving. How much of each food must be bought to produce the minimum cost per serving? Okay, so again, we're trying to figure out first what we're trying to maximize or minimize. Here we're actually minimizing, and we're trying to minimize cost. So I want to look for x being equal to my number of units for food A, and y being my number of units for food B. And I want to minimize my cost, so I'm going to look at my equation, or look at my situation here. I'm going to look at what my cost is for each unit. I know A costs 18 cents per unit, and B costs 12 cents per unit. So I know my minimization objective here. I want to minimize the objective quantity of 0.18x plus 0.12y. So I'm trying to minimize this objective. Now I need to come up with my constraints. So I have the constraints of grams of protein and grams of fat. So I know here that I need at least 30 grams of protein and 20 grams of fat. And I know the protein and fat content for each of the types. So that means I'm going to kind of organize my data here, and I'm going to say, well, let's put proteins with proteins and fats with fats. So I know I'm going to have at least 30 grams of protein. At least 30 grams of protein. So let's look at our protein for each. I know food A contains 2 grams of protein, and food B contains 6 grams of protein. So I know I'm going to have a protein constraint that says I have 2 grams for food A plus 6 grams for food B. That has to be at least 30. That means it has to be bigger than or equal to 30. Now I also know my fat content for each. My fat content for each is 4 grams of fat for food A, 2 grams of fat for food B, and I need to have at least 20 grams. So I have a second constraint of 4 for every unit of food A and 2 for every unit of B. Has to be bigger than or equal to 20. Now I also have this last restriction that says I have a contract requiring that at least 2 units of food B be used per serving. That tells me I have a constraint that my food B, which is Y, has to be bigger than or equal to 2. Now of course I also have the constraints that tell me I'm dealing in the first quadrant. So I've graphed my inequalities here. I have Y is greater than or equal to 2, and 2x plus 6y is greater than or equal to 30 is this line. and 4x plus 2y greater than or equal to 20 is this line. You can see where my intercepts are and so on and so forth. Now I need to figure out where I want to shade. So let me change to my highlighter. I know y has to be bigger than or equal to 2, so I know I'm going to shade above that horizontal line. I also know that 2x plus 6y has to be bigger than or equal to 30. So if I tested the point 0, 0, 0 is not bigger than 30, so I know I'm going to shade above that line. Because that's opposite the side of 0, 0. Then I also have 4x plus 2y is greater than or equal to 20. I know that 0, 0 is not contained in that solution, so I'm shading above. So you can see here where my feasible region is. My feasible region is contained where all of these inequalities overlap. I'm going to erase just a tiny bit more so you can see those corners a little better. Now, we have to find our corners. To do that, I need to solve some systems of linear equations. So I need to find the intersection here, and here, and here. So I know the intersection, sorry, too far. I know the intersection here is the intersection between y equals 2 and 2x plus 6y equals 30. So if I know y equals 2, and I have 2x plus 6y equals 30, just plug in y equals 2 to that equation. So 6 times 2 is 12. So I have 2x plus 12 equals 30. If I subtract 12 from both sides, I get 2x equals 18. So x equals 9. So I know I have the point 9, 2 here. Okay, this point here was the y-intercept of my opposite equation. The y-intercept there is the intercept of 4x plus 2y equals 20. So if I cover up the x term and solve for y, I know that that is 0, 10. To solve for this corner here, I know I need to solve the system of equations that are represented by my two equations of my constraints. So I have 2x plus 6y equals 30, and 4x plus 2y equals 20. So I'm solving that system of equations. Remember, I can do that easily with matrices, doing A inverse B. So 2, 6, 4, and 2, and 30, and 20. Solving that system in my calculator, I get 3, 4. So that's my last corner. Now I'm trying to minimize with these corners. So I need to plug in each one of these values. To my objective equation. My objective equation is 0.18x plus 0.12y. So 0.18x plus 0.12y. So I'm going to plug in 0, 10. 0.18 times 0 is 0. 0.12 times 10 is 1.2. So the value at 0, 10 is $1.20. 3, 4. 3 times 18 is 0.54 plus 0.12 times 4 is 48. That gives me $1.02. Then my last point is 9, 2. And 0.18 times 9, let me put that in my calculator real quick, is $1.62 plus 24 cents is $1.86. Be careful, here I'm looking for my minimum. My minimum occurs at 3, 4. So I know I need 3 units of food A and 4 units of B. Now it's worth noticing that this region here is unbounded. That means that this region here will keep expanding. That will keep expanding upward. So there is not going to be a maximum within that feasible region. We can only find a minimum here. Alright, these are the application problems from